Okay, hello everyone. Good morning. Okay, so welcome back to our lecture. All right, so this week we don't have tutorial, okay, because it's on interrupts, all right, and we're only covering interrupts today. So I think it is more appropriate if we have that tutorial next week. Okay. So today we're going to cover the topic on interrupts. Okay, and of course it is something that you are familiar with, all right, from your exposure to the Arduino, all right. Of course, this is a far more powerful controller, so we're going to understand how this controller deals with interrupts, and then we look at the programming aspect of it, and finally, as always, we will end off with the demo for the lab. All right. Let me share my screen, and then we can get started. Okay, can everybody see my screen? Okay, thank you. Okay, so let's get started with the Cortex M0 Plus exceptions and interrupts. So we are going to be covering this sort of main topics here: the concept, okay, what happens during interrupts, okay, Cortex M0 specific interrupts, and we're going to be looking at some timing behavior, all right, and then finally we're going to look at the programming aspect of it. Okay, so this is the hardware that we sort of reviewed last lesson, where we had a switch. Okay, we had a switch, and we sort of looked at the active high, active low configuration of this kind of hardware. And that is, of course, very important, because as computer engineers, you need to be aware of how the hardware is designed so that you can write the appropriate software to handle it. Okay, so we saw this last week, so I'll not go through that again. Since we already have a RGB LED on board, okay, so that will generally help us in most of the labs. Okay, in terms of inputs, we need a switch. Okay, so for this week's lab, all right, we need to do a few things. Firstly, you need to start the soldering of the connectors onto the board. Okay, you don't need to solder all if you don't want to. I'll just show you that particular row, okay, that you need to for this week's lab. Okay, but if you want to one-shot solder everything, is also fine. Okay, as I mentioned, soldering is very, very important. If you don't do it properly and it starts to spill over and so on, it might cause short circuit within the pins, okay, or you can even damage the board. Okay, so for the soldering part alone, you can always approach someone else in the lab who is more proficient, okay, and can help you with the soldering part. Okay, it's not that you should not learn, but to practice, you can always get spare boards, spare proto boards and components, and you can practice on your own. Okay, but don't practice on the KL25Z board. Okay, so for this week's lab, we need to do that. So I will cover that again in the end of the lecture. Okay, how do we detect a switch being pressed? Okay, so what we did last week was the polling approach. Okay, so if you remember the code that we went through, it was basically checking, okay, for a particular pin whether it becomes one or zero, and then we perform the appropriate action. And the other more efficient approach, which we also know, is the interrupt service routine approach. Okay, where you have some specialized hardware within the controller itself, and this hardware actually helps us to detect events, and when those events occur, it allows us to run specific code. Okay, of course, it is very, very efficient because it only is activated when the event happens, so it's also very fast. Okay, and it scales well in a sense that it allows you to add on more sort of real-time response capabilities to the system, but of course, as always, you are limited by what the hardware offers. Okay, if your controller only has maybe 3 or 4 pins that can have GPIO interrupt, then you are limited by that. Okay, so the limitation is in the hardware sense, but it does give you a lot of efficiency when you want to quickly react to events. So the first, so this is the idea that I think we are familiar with, all right, where you generally have a main program or a main loop. Again, that main loop will run, and when that loop is running, suddenly an event occurs. So you can say it's a external or could be internal, okay, and it sort of triggers this interrupt. And once that happens, you need to perform some hardwired processing. Okay, so what is this hardwired processing, or what are these activities? Okay, can you all share with me? I think we discussed this. I think about 2 lectures ago. What are the things that your controller must perform or must do the moment it detects an interrupt? Okay, so you can go to the poll link and you can just share your thoughts on this. Save the state of the current activity. Yeah, correct. Save the context of the program. Push to the stack, correct. Place current activities on the stack. Yeah, so you all get the idea, right? You know what is supposed to be done. All right, so generally what you're supposed to do is you need to make sure that you are able to sort of take a snapshot of what you are doing. Okay, so when we say take a snapshot, means I need to save the context of the program. So that means your program counter, your register values, and all this information. So where do you save it? You have to save it onto the stack. Okay, and then once you return from the interrupt, you will pop it from the stack and you can resume from where you left off. So that is the what I call the hardwired activities. All right, and this we say is hardwired because you don't have to write any code to do it. It is already sort of handled by the interrupt controller block itself. Okay, the hardware does it for us. Okay, so everything is in the background, and all we need to focus on is we need to make sure that I perform the right configuration, okay, to detect whatever I need to capture, whether it is a timer overflow, whether it's a push button, whether it's a signal coming in on my serial port. Okay, whatever it is, I need to perform the correct configuration and all those settings to make sure my hardware is ready to capture that event. Okay, once that event happens, all these hardwired activities will automatically go on in the background. Okay, and then I will jump to my ISR. Okay, and then I will perform what is really necessary, and then I'll come back. Okay, and we also talked about the concept of ISR being short and focused, because you want to make sure that the rest of the backend processing can be done in the main code, okay, or in some other tasks and so on. Okay, so that is the whole idea of these interrupts. Okay, in terms of triggering, okay, we can say that it could be triggered by a hardware or signal that could be external or it could be internal. Okay, so internal means things like your timer blocks, okay, overflow, okay, or some other event happen within the maybe do a DMA transfer or things like that. So within the system itself, you can generate interrupt. External things like your GPIO interrupts, your serial port suddenly receiving a data and so on. Okay, it is asynchronous because it can happen anytime. Okay, and the moment it happens, you run the appropriate software for it. Okay, so this is basically a very fundamental mechanism that actually allows us to be responsive. Okay, so even without a operating system, you can still have a good level of real-time response because of these interrupts and their capabilities. Okay, so this is the idea. This is what we're going to be looking at today, how we're going to use the switch, okay, to trigger an interrupt, right? And when the interrupt occurs, I will sort of have a variable which I will also increment, okay, and at the same time, I will also be writing or updating a LED, the RGB LED. Okay, so this is the lab requirement. Okay, and I will show you a demo of it later. Okay, Cortex M0 plus interrupt. So now what we covered, what we discussed just now is the general idea of interrupts. All right. So of course that applies to all controllers. Okay, but when you take a specific controller and you want to start developing on it and you want to enable interrupts, then you need to look into that controller's interrupt capabilities and the configuration, all these settings. All right. So that is what we're going to look at now. So in terms of the Cortex M0 Plus, it is also the same as before. Okay, where you have interrupts. Okay, and generally we say interrupts are asynchronous because the hardware event can happen anytime. But you also have this concept of software interrupts. Okay, and generally we call them exceptions of force. All right, for example, your program tries to access instruction or tries to access an address that it is not supposed to. Okay, then that could lead to a memory fault. Okay, or some overflow occurs for some instruction. Okay, so this could be what we call exceptions, and we say these are synchronous because they happen in relation to you executing some code. Whereas the asynchronous versions are things related to some hardware event happening. Okay, and the interrupt service routine is basically there to handle these events as and when they happen. Okay, so before we go into that, let me just do a quick sort of recap and revision on what we did last week. Okay, can you look through your data sheet? Okay, like I said, you always have to have a data sheet standby. All right, and tell me what this line of code is going to do. Okay, I'll give you a few minutes. You need to look back at the data sheet. All right, go and find this register. Okay, if you already have done last week's lab, you would have already have some experience with looking at what are the SCGC registers, okay, or SCGC5 in particular, okay, and we are doing some bit masking here. So I want you to look back at that and tell me what this line of code is going to do. Okay, so I'll give you a few minutes to open up your data sheet. Enabling clock for port D. Okay, any other answers? Clock enable port D. Okay, so another person also had the same conclusion. Does anybody else have a different thought about it? Okay, so I think everybody can agree that this is to enable clock for port D. So now let me just make sure that everybody sort of understands why this is the case. Okay, in case you are still not sure, or in the last lab you were maybe doing a bit more eye power. Okay, so let's look at this. So in this code over here, what is happening? Okay, so this SCGC5. So let me open up to SCGC5 first. Okay, and let's look at that. Okay, so this is the SCGC5 register, and this is the same register you used in the lab. And as what we saw, this is to control the or enable the power to the different ports that we have, port A to port E. So that is the first thing. Okay, so we understand what SCGC PI is for. Now in this code here, what we're doing is we're doing an OR operation with this value. Okay, so what is this value over here? So let's look at that. So if I look at this, this is the lower 3 hex 0. That means this is from bit 0, 0, 0, 0, then 0, 0, 0, 0, and 0, 0, 0, 0. So this is bit 0, okay, all the way to bit 11. Okay, total 12 bits. Okay, and this is the bit 12. Okay, this is the bit 12, and that bit 12 is 1. Okay, so it's 0001, that first hex digit there. Okay, so bit 12, I'm setting it to a 1 because this is a OR operation. Okay, so when I set bit 12 to 1, okay, basically what happens is bit 12 is this. So as you can see, bit 12 relates to port D. Okay, so I'm enabling power to port D. Okay, so that is what that line of code there does for us. Okay, so if you were still unsure, okay, I hope that now you are in a better position. Okay, so you must get used to this kind of programming style and technique and all this bit masking and so on. Okay, now let's move on. So coming back to the interrupt controller, okay, we have a lot of interrupts, all right, which can trigger the controller. Okay, so this is the main processor core over here, and we can have a lot of peripherals, a lot of subsystems that can all trigger the or request attention from the controller. So how do we manage so many different peripherals and subsystems at the same time? That is where the NBIC comes in. So the ARM controllers have this special hardware called the NBIC, Nested Vector Interrupt Controller. And what it does is it sort of gathers all these interrupt requests from the various peripherals, and then using its then you look at how we have configured the interrupts, what is the priority, and based on that, it will send the appropriate sort of interrupt request to the processor. Okay, so all our interrupt requests go to the NBIC, and the NBIC from there channels the appropriate one based on the priorities, and then sends them to the controller. Okay, so this is basically how or the way in which the Cortex M0 Plus handles. Okay, generally all ARM controllers have this NBIC built in to do this sort of interrupt control. Now, interrupt sources. Okay, so let's look at what are all the different things or different peripherals that can generate interrupts. Okay, so for this, I would like you to open up your datasheet again and look for this table 3-7. Okay, I want to look at this table 3-7. Okay, so again, why it's always good to go back to the data sheet is because you have the full set of information there, correct? And what I'm showing here is just a part of the table. Okay, so let's go to our data sheet, table 3-7. Okay, so this is the one, interrupt vector assignments. Okay, so if you can see, you see here that the first 16 interrupts, okay, the first 16 interrupts are the ones that are what we call core vectors. Core means they are critical to the operation of the whole controller. You cannot touch them. Okay, they are for very important things such as your stack pointer, your program, initial stack pointer, initial program counter, NMI, hard fault, and so on. Okay, so these are all reserved, and 16 onwards is for all the peripherals. Okay, for all the peripherals. So you have your DMA, your I2C, UART, and so on. Okay, so each of them, okay, have been assigned a particular address. Okay, so you can see down here that each interrupt source has been assigned a address and a number associated with it. Okay, and these are the always stored inside the interrupt vector table over here. All right, so if you look at this, what you observe is each of this address space is 4 bytes. Okay, if I come back here, okay, you can see that for each of this address here is all 4 bytes of information. Okay, so at each address I store 4 bytes of information, and that 4 bytes of information is what is actually the actual address of where the interrupt handler is located in memory. All right, Now let's look at how this works. Okay. Now let's assume that right now I configure my port A interrupt. Okay, let's assume I configure my port A interrupt. All right, that means I want to capture, okay, some event on port A, some particular pin. All right, so somewhere in my code, okay, I will have a port A IRQ handler. This IRQ handler is basically your ISR, interrupt service routine, but in here they call it IRQ handler. Okay, so I would have written that somewhere in my code. So that is what you see over here. Now, where is this going to be in your full memory? You do not know, all right? Because you have set aside, or the linker has already set aside a space for all your code. And of course, as you write your code, this starting point of these various functions will get shifted around. Okay, so we do not know the exact starting point of where the handler is. All right, only when you are ready to compile your code, okay, and then you know the address, okay, because during compilation and linking, the address is known based on the mapping to the memory space. So now let's assume that this address is just, okay, just give a simple address A000, okay, or 0000, a 32-bit address. Okay, let's assume that that is my starting address of this port A IRQ handler. Okay, of course, like I said, this is not fixed. You can always shift up and down depending on how big your code is. Now, when I compile my code, what your compiler will do is, once it knows that you have written a port A IRQ handler, okay, it will take this address, okay, it will take this address and put it in this location here. That means you'll go to this location 000000B8 and put this address there. Okay, so in terms of the memory, okay, at that point, what you will see is, okay, if I look at the memory here, if I look inside the data over here, I will see this value. Okay, 0x A0000000. The same thing happens for every handler that you're going to write. So when the interrupt eventually happens and you get triggered, okay, so this is part of the hardwired activities we talked about earlier. So the hardwired activities, just now, most of us, we discuss only the part where we save the context, correct? But after while we're saving the context, you also need to make sure you are able to jump to the correct handler, correct? So that is where this part also comes in, which is also hardwired. That means your controller will automatically jump to the appropriate vector address based on the interrupt that is triggered. Take this information, okay, take this information which is inside this location, that means this address, and I will put it into my program counter. Okay, so once I know that this value is in my program counter, that means when the next clock happens, I will start to execute the IRQ handler. Okay, so that is basically why you set aside only 4 bytes of space for each IRQ entry point in the vector table. Okay, so this is standard across all the peripherals. Okay, and most controllers also do the same thing as what we discussed here. That means what they do is they store the address of the handler inside the vector table. All right, and when the interrupt occurs, your controller will go to the appropriate entry point in the vector table, take that address that is stored there and update the PC with that address. So you will now be able to start executing the handler. Okay, so this is all part of the hardwired activities that we discussed earlier. Okay, so that is the general idea of how a vector table is populated, all right, and how the interrupt is actually handled by the controller the moment the trigger happens. Now, the next thing is how do I allocate priority? Okay, so in some controllers, you may already have a fixed priority based on maybe the positioning in the vector table. All right, so if you remember, your Arduino Uno follows that. That means based on your entry in the vector table, that is sort of implies the priority. Okay, but in our M0 Plus here, basically you have the ability to configure each priority individually. Okay, so you can see down here we have from IRQ 0, okay, from IRQ 0 all the way to IRQ 31. So these are all the interrupts. Okay, so if you look back over here, okay, the IRQ 0, IRQ 31 is basically talking about this number here. 0 all the way to 31. This is the interrupt IRQ number, and you can see this is only applicable to all the non-core vectors. So these are all the interrupts that are tied to peripheral subsystems. So you can configure the interrupt for all of them depending on what value you put in the table there. Okay, so now let's look at how this thing works. Now you have 8 different interrupt priority registers. Okay, 8 different registers, IPR0 to IPR7. And in each register, you are able to configure 4 different priorities for 4 different vectors. So for example, IPR0 is to configure for IRQ0 up to IRQ3. Okay, if I want to configure, for example, IRQ18, okay, then I need to go to IPR4. Okay, now what values do I put in? So if you look at it, each of it is actually an 8-bit value. So each of it is an 8-bit value. But out of the 8-bit value, I only use the upper 2. The most significant 2 bits are the bits that are used to configure the priority level. And the priority level is basically 0, 1, 2, or 3. Okay, where 0 is the highest and 3 is the lowest. Okay, so this 0, 1, 2, 3 also corresponds to setting the 8-bit value, okay, as either 0, 64, 128, or 192. Okay, why? Because 0 means all is 0. This 64 basically means it is 0, 1, then 6 zeros. Okay, why 6 zeros? Because for each of these 8 bits, okay, is broken up into 2 and 6. Where the upper 2 bits are used and the lower 2 bits, lower 6 bits are not used. Okay, whereas 128 is 1 0, then 6 zeros, and this is 1 1, then 6 zeros. Okay, now of course we do not need to explicitly write code to do all the bit shifting and masking, all of that. We already have a built-in sort of macro given to us, which is the nbig set priority. Okay, so for all of this, there are actually a lot of readily available either library functions or macros already there in the libraries. All right, and we can just tap on them to configure all of these settings for us. Okay, so later in the example code you will see. All right, now before we set okay, while we're setting priority, we also need to enable the IRQ. All right, so to enable IRQ, we also have these functions here. Enable IRQ with the number that you want. If you do not want, then you disable the IRQ. Then there is another 2 functions here: set pending IRQ and clear pending IRQ. Now, this set pending IRQ is not used, but it is basically in a way used by the nbig controller to say that IRQ is there, okay, but it is not yet serviced. All right. Whereas clear pending IRQ means the IRQ was pending, that means it was waiting, but now you have already started to service it. Now this is again part of some legacy code, so this is actually not necessary, but I will still show it to you later on in the example code, all right? Because if you are probably searching for some reference code, when you're doing your work and so on, you will probably see this statement inside the IRQ handler, but you will see that even if you remove this, it is fine. Okay, because the interrupt request is automatically cleared the moment you enter the ISR. Okay, but this is their part of the legacy code, okay, from the earlier days when they developed the library. Okay, then there is a global interrupt. Okay, so global interrupt enable disable is to have a mask across all interrupts, whether you want to totally block out everything or enable. All right, and again, you can use the built-in API functions, the enable IRQ or disable IRQ. Okay, so these are the important things, okay, that you need to take note of. Okay, in terms of priority, okay, like I said, what we can adjust are those for the non-core vector, the peripherals. Okay, for those you can adjust. Then the rest of them, the core ones, are fixed. Okay, so the highest priority is of course always your reset vector, then followed by NMI and hard fault and so on. So those are the ones that are already fixed, but we do not have to worry about them. That is already part of how the controller behaves. What we can configure are those related to the peripheral systems. Okay. Now, of course, there is always a case of nested interrupts. All right, and our controller definitely supports nested interrupts. Okay, so if I have multiple interrupt requests coming in, what happens? All right, so if the new priority is higher than the current priority, okay, then there is a preemption. Okay, that means the current interrupt will be kept on hold and the higher priority one will take over. Okay, if the new priority is lower than or equal to the current priority, then the new one is held in a pending state. Okay, and once the earlier one is complete, then the pending one will take over and run its ISR. Okay, so again, all of this is in the back end. All right, we do not need to worry about the details of how it's happening. The controller does it for us. Okay, so now let's look at the program requirements. Okay, and what we're going to do. Okay, so in this example that I'm going to show you, what I have done is to configure a switch, okay, to control the ISR. Okay, and as you control the ISR, I'm going to update a variable, account variable, and at the same time, I'm going to control the blinking of a LED. All right, but in the lab, you're supposed to do something else. You're supposed to control the RGB sequence. Okay, that means you need to go from red to green to blue and so on. Okay, but in the demo here, I'm just going to show you a simpler version where you just blink the LED or switch off the LED. Okay, based on the interrupt, but you can see that the interrupt does sort of increment the count variable every time it is triggered. Okay, now which are the ports I can use, okay, for interrupts? All right, so we know that, okay, from last week's lesson, our KL25Z has a lot of ports, port A all the way to port E, okay, but not all the port bits are available. All right, so that's the first thing. All right, so if you look back at the multiplex table, you'll be able to see that not all the port pins will be available for us to use. All right, and the second thing is in terms of interrupt, okay, we only have port A and port D that support interrupt. All right, so that is why in your interrupt vector table, you only see the interrupt handler entry point for port A and port D, the last two. Okay, so only these two ports support interrupts. Okay, so you can't use other port pins if you want to use interrupt features. Okay, so now let's look at the KL25Z physical setup. Okay, so for this physical setup, what you need to do is you need to first solder the pins. Okay, so you can see down here, all right, on the board. Okay, okay, so give me a minute here. Let me set up my hardware here and I'll show you in a minute. Okay, so this is the physical setup. Okay, so you can see down here, what you need to do is, okay, so this is the board. Okay, so the first thing is, if you want to, so here I have all my connectors soldered over here. All right, if you only want to solder enough for this week's lab, then you just, when the board is facing you, okay, okay, you can see that the touch screen is on top. I mean the touch sensor, and this is the bottom left of the board here. Okay, with the connectors below. So this is the place where you are going to connect the switch. Okay, so to connect the switch, okay, these are the pinouts already given to us. All right, where we are going to take the bottom, the left row, fourth from bottom is the ground, and the one beside it, second from bottom, is the port D pin 6. So we're going to connect the switch to port D pin 6. Okay, so now how do I connect up my switch or wire up my switch? Okay, so this is the switch given to you. Okay, so this switch given to you basically is a simple push button switch. All right, and the only thing you need to do is you need to solder wires to both the LEDs. Okay, so this one is fairly easy. Just don't keep the soldering iron there and then start watching TikTok or something. Okay, you melt the whole thing away. All right, so just make sure that the moment the solder has melted a bit and the thing is secure, you can remove the soldering iron. Okay, yeah, but in any case, if you suspect the switch may be faulty, you can always do a swap. Okay, just ask the TA and they will do a exchange for you. All right, so this is the only piece of hardware you need for this week's studio, this week's lab, and you need to of course solder at least this part over here, the bottom left of the connectors. All right, so that is the experimental sort of setup that you need to do for this week's lab. Okay, so once that is done, of course, you have your switch configured. Now, if I look at this hardware design over here, okay, what do I observe? Okay, you can see that this is port D pin 6. All right, and what I've connected is I connected it to one end of the switch, okay, which is this port over here. Okay, and then the other end of the switch, so if this is the switch, okay, then the other end of the switch connected to ground. All right, that is basically the connection that I have. Now, this doesn't seem to be like anything that we saw earlier, correct? When we look at the switch connections and the design of pull up and pull down and so on. Okay, so what is missing here? What is wrong over here? If I try to read this pin value, okay, if I configure port D pin 6 as input, okay, and I try to read, what is the value I will get? What is the voltage value I will get? Any idea? Yeah, correct. It is a floating pin, correct? It's a floating pin. It's not connected to high or low, which means you could get some random value, some noise and things like that. Okay, so it is something is missing here, correct? So if I want a switch to be correctly configured, okay, I need to make sure that it is by default either pulled up or pulled down. Okay, but this is by default seems to be floating, all right, but yet it is correct, okay, because of some internal configuration we will do in a while. Okay, but in terms of the connection, this is what you need to do. Okay, but do take note of this. Okay, you must never connect a switch like this unless you know that there is a way to do some pull up or pull down later on. Okay, which is what we will come to in a while. Okay, so the idea of the lab is I want to break up the entire program into sort of pieces, into threads, and the whole idea is in my main loop, I will be first doing some initialization. So that part, I think you can sort of relate to from what you have done before. So in the past lab, you only initialize the GPIO to be output, okay, to control the LEDs. Now we also have a switch, so you need input and output, and then the additional stuff is the configuration for the interrupts. Okay, and then inside the interrupt thread, okay, we want to update our count, and of course at the same time, while we're updating the count, we also want to use that to update the LED. Okay, so the updating of the LED can be done in the ISR or can be done outside. Okay, so like you mentioned, we try to keep everything simple in the ISR and let the main loop handle the rest of the things. Okay, so I think the important thing is the interrupt handles the count update or some status update, and then the main loop can handle the other stuff. Okay, so whenever you have variables that are shared, okay, there's two things. One is the volatile keyword, I think which we have seen before, but we will look at that. At the same time, atomic. Okay, we need to make sure it is atomic. Okay, so we will look at both of this and try to understand what we need to do. Okay, so what is a okay, so when you declare a variable normally, okay, so when I look at this integer x goes to 0, I declare this variable. Okay, this statement will tell me that somewhere in memory there will be a variable called x, and I declare and initialize it to 0. Okay, somewhere in memory. Okay, now when I execute this statement, x equals to x plus 1, what happens? All right, so in a ARM controller, okay, is a RISC system. That means whatever operations that need to be carried out will only be carried out on the internal registers. It cannot directly act on memory. So I need to first take a copy of x, put it into an internal register, okay, then do the increment. Okay, do the increment after that. So after I come into internal register, so if I look at this code over here, it will break up into two things. First, I will load from wherever x is pointing to into R7, register R7. Okay, and then I will do an add. Okay, so I'm just trying to give you some pseudo code. It's not actual ARM assembly language here. So I say add immediate value, for example. So R7 add with 1, put back into R7, and then I do a store. Okay, into wherever x is pointing to, for example. Okay, now in most cases, what happens is this store may not happen immediately after the operation is done. Okay, why? Because you may use x in other places in the code. Okay, so you may keep it within the register, you may keep it within the cache. Okay, so we're not going into the cache design here, but cache is just another sort of memory region, okay, within the processor that can also help to keep some variables that are accessed regularly. Okay, so you may store it within the processor space itself without necessarily updating the actual memory. Okay, you will still do it, but you might do it a bit later depending on how you have written the code. Okay, so this of course works fine. All right, in most cases you don't have an issue with it. Now if I have the same situation, all right, but now I have ISR that also can update x. So x is now a global variable. Okay, I mean it's also global variable before, but now x can also be updated in the main code, and it can also be updated in the ISR. Okay, so in this case, what happens? Now, if I look at my main code over here, okay, I am doing a read over here. So when I translate this to assembly, what happens? You will say load into register R7 from wherever x is pointing to. Okay, or the actual memory address of x. Okay, and then what do? I check. So I say maybe branch if not equal R7 0 to some other location. Okay, then I have other code. Now the key thing is all this code, for example, maybe did not reference x in any way. And as far as the compiler is concerned, what it will see is this is the line where I do a read, okay, from X. That means I read from the memory, okay, and all the subsequent code, there is no write to X. Okay, if all the subsequent code there is no update to this variable X, all right, then the compiler, of course, is smart. Okay, it always tries to optimize the usage of the space and the performance. Okay, so when it sees that, hey, I read from the memory in the beginning, but in the rest of my code there is no instruction to update this memory. So since there is no instruction to update the memory, that means the memory should not have changed. So if the memory should not have changed, then I do not need to read from the memory again in subsequent instructions. I just keep on reading from R7. Because R7 is already holding X and X has not changed. Okay, so that is the behavior of the compiler. Okay, most compilers will do this. Okay, they'll optimize for us. Okay, now of course, if you turn off optimization and all these things, then generally everything gets affected. All right, but if you want to keep the optimization, all right, but you just want to handle this issue, all right. So what is the issue? Okay, the issue is when I have the ISR that can also update X. Okay, this is not captured in this entire sequence here. Okay, because the write to X is not happening in this over here. So when that is the case, okay, when that is the case, then what happens is, okay, even though X may be updated in the ISR, inside my main, I'm still reading only from R7. I have not updated R7 with the new content of X. Okay, so that is the issue that can happen. Okay, I think in EPP2 we did expose this to you, and you saw this to be an issue. All right, so the solution to this is to declare the variable as volatile. Okay, when you declare a variable as volatile, what happens? You are telling the compiler that this particular variable, okay, the contents of this can change regardless of explicit write to it. Okay, an explicit write to it. That means it doesn't have to be that I have an instruction that says X equals to something. Then only it can change. It can happen through other means as well. So that is the general idea of what it means when we say it's volatile. So when we say it is volatile, that means everywhere in the code where I am referencing X, okay, I will always have to do this step. That means I always have to take the latest value from memory, update my register, and then use the new updated value. So I will force the compiler to do this memory access for me the moment I declare the variable as volatile. Okay, so sometimes you may see that, hey, I never declare volatile, but it still works. No, it still works. Okay, then again I say it's only it sort of depends on what else you are doing in your main code over here. Okay, so if in your main code it is written in a way that there is also read-write access. Okay, then there is a chance that this load from the memory is again happening. Okay, somewhere else in the code. So when the ISR gets updated, you are also able to get the updated value. Okay, so you might still see that it works, okay, even without volatile, but again, it is a good practice to have volatile if you have a situation where variables are updated, shared variables are updated in the ISR, and you want them to be read in the main program. Okay, so that is the whole idea of the sort of programming overflow. So we need a main program, okay, to do all the initialization, everything. Then we need to define the switches, and then finally the LEDs. Okay, and then we also need to configure the microcontroller accordingly to make sure we are able to respond to the interrupt. So we need to, so in the last lecture and the lab, we also saw how to do some basic configuration, the clock gating, the input or output, and so on. Today we'll look at a few others. Then we also need to set up the NBIC. okay, and also enable interrupts. All right, so in terms of the port module, okay, what we need to do is we have all the ports. So like I said just now, port A and port D all have interrupt capability. So we need to make sure that we configure that particular pin that we want to have the interrupt capability, and that is the PCR register. So if you remember the PCR register, we actually used it in the last lab, and in the last lab we used it for the mark setting, where we say that each individual pin we can configure the appropriate peripheral that you want to use, whether you want to use it as GPIO or a timer or a UART or whatever. Okay, so if you look at the mux function, then we'll also be looking at the in today's lab, we'll be looking at the other function, which is configuring of the interrupt. Okay, then we'll also be looking at the interrupt status flag register, okay, to know whether interrupt has been detected or not. Okay, in terms of the pin control register, the PCR register, okay, so this is what we have. Okay, so let me come back here. Okay, so this is the pin control register that we saw, and this is the bit 8, 9, and 10 were what we use for the mark setting. All right, and if you look further up here, bit 16, 17, 18, 19 is for the IRQ control. Okay, for the IRQ control. So that is what we need to do here. So if you look at the sort of values you have here, you can configure interrupt, okay, based on these options here. All right, so we are not going to do DMA, okay, so we can leave this out. Okay, and what we can do is this. These are all the different options on what kind of external signal will generate interrupt. Okay, is it when it's logic 0, logic 1, rising edge, falling edge, or both edges? All right, so these are all the things that we can actually configure and that particular pin to capture the appropriate interrupt. Okay, so these are all the values we can put inside the IRQC over here. Okay, so let's go for a break now. Okay, okay, now it's 10 o'clock. Okay, we'll go for a 10 minutes break. When we come back, we will look at the code. Okay, we will look at all these configuration and settings, and then we will look at the demo, and we'll understand exactly what is going on. Okay, so let's go for a 10 minutes break. Okay, I'll see you back here at 10:10. Okay, so welcome back. Can you all see the screen? Okay, thank you. All right, so let me just give an overview of this week's lab first. So in this week's lab, we're basically going to be doing what we talked about, which is to develop our own ISR, okay, to control the LEDs based on the switch. Okay, so the hardware is just like what I mentioned just now. Okay, where you have a single switch connected between port D pin 6 and the ground. Okay, and the switch basically you just need to have 2 wires soldered to it. That's all. Okay, and you're supposed to create a new project, okay, and develop the port D IRQ handler. Okay, so I'm actually going to be showing you this so you understand what we're going to be doing and how it works. All right. So inside your main code, you should have something like this where you initialize the basic peripherals, and then over here you can do other stuff where you're waiting for some flags to be updated, okay, from the ISR. Okay, and this is the switch. And in terms of the demo, okay, you are supposed to show that as you press the switch, your LEDs go in sequence, that means from R, G, B, then back to R, and so on. Okay, so that is the demo aspect. Okay, so let me go through the code part so you understand what is happening. Okay, so in terms of initializing the GPIO, okay, what do you have to do? Okay, so the first thing is, okay, you need to enable the clock. Okay, so we have seen that last week. Previously it was only port B. No, last week also port B and port D, correct? And since we are using which port are we using? Yeah, port D. Okay, the switch is port D, so it is already part of the initialization here. Okay, so both port B and port D need to have their clocks enabled. Okay, and subsequently you enable the three, or you configure the mux. Okay, so if you remember, the PCR, okay, is a register that has many functionalities. Okay, so if you look at the PCR, okay, one of the things is the mux setting. So the mux setting is basically to configure the multiplexing option. All right, and by default, the mux 1 is always GPIO. Okay, for those GPIO functions. Then of course the other peripherals, you need to look back at the mux table to select the correct number. Okay, but as long as it's GPIO, then you can safely put it as just mux 1. Okay, and then the last part is the data direction registers. Okay, so this is all for the LED. Okay, so for both the red and green LED plus the blue LED. Okay, so we do it separately because you have the port B for the red and green and the port D for the blue LED. Because this is basically for the initialization of the LEDs. Okay, how about the switch? Okay, so now let's look at the switch. Now the switch is more things. So the switch, firstly, we are enabling the we're using port D, so we need to first enable clock for port D. Now, of course, you may ask, why do I still do this here? Okay, even though I already have a earlier function that also enable power to port D. Okay, so it is fine to do it 2 times. Okay, in my opinion, because if you're talking about reusable code, right, there is a chance that maybe in another project you're going to use the switch, but you're not going to use the LEDs. Okay, so if I assume that the LED function is always going to be called, and then I try to run this code, and then I realize the switch will never work because I never enable power to port D. Okay, so in terms of creating libraries and creating reusable code, is good to write it in a way that you do not assume that somebody else is going to do it. Okay, so I know that my switch requires port D, so I'm going to enable port D. And since I use, as long as you use the proper bit masking techniques, then you're fine. Okay, so the bit masking and the OR and AND, all this stuff is important. Okay, again, because you're going to have a lot more functions, a lot more code as you go along. And if any one of those functions, instead of using bit masking, you do a direct write, okay, then you're going to override everything that you did earlier. And then you realize suddenly everything is not working. Okay, so this is very important. So by using bit masking, you do not interfere with other settings done in other earlier functions. All right, so that's the first thing. Now the next thing is the PCR. Okay, so the PCR, okay, there's a few things that we need to do over here. So now let's look at this code over here. Now this mux1 is to configure my multiplexing to say GPIO. Now the next two, okay, so before I look at the next two, let me come here first. Port PCR IRQ C0x0A. Okay, so what does this do? Okay, so let me go to this. Okay, so if I look at the definition here, what it does is, okay, again, like I said, we will always make use of all the built-in macros to help us. All right, so what it does is when I pass in a value, it will shift it by a certain amount and do a masking. Okay, so it will shift by how much? It will shift by this shift here, shift by 16 and do a masking to take those 4 bits. Okay, why shift by 16? Because your values IRQC are in the bits 16, 17, 18, 19. Okay, so that macro there, it automatically, whatever value you pass it, it shifts to that location that is mapped to IRQC bits and does the appropriate bit masking for us. So it handles all of that for us easily. Okay, so we just make use of that macro to set whatever IRQC IRQ value we want. And this IRQC is basically the IRQ configuration. That means how do I want this to trigger interrupt? Okay, so these are all the options. Now, what have I done in my code? I have given a value of 0x0a. Okay, so 0a is 1010. So if you look back here, 1010 is to interrupt on falling edge. Okay, so I want to interrupt on falling edge. Okay, now when I say interrupt on falling edge, so what is going to happen? That means if I look at my design here, okay, that means by default it's supposed to be high, and then it interrupt on falling edge. Okay, so whenever the switch is closed, I'm supposed to interrupt. All right, so we already know the switch is designed such that it is like this. Okay, and this one goes into the port pin. All right, so that means by default, this one must be a 1, and when I press, it should go low. So if I want this pin to by default be high, okay, plus VCC, okay, I need to do a pull up. Okay, I need to do a pull up, and that is actually the other two configuration here, PS and PE. Okay, so this PS and PE, what is that? Okay, so if you look here, back at our data sheet, okay, the PS and PE are also part of the IRQ, the PCR register. So PS and PE are here. So let's go down here to have a look what it means. Okay, so what we are doing is we are setting both of this to 1. So when pull enable is 1 means internal pull up or pull down is enabled. Okay, so this is what I mentioned earlier. So you are going to use the internal hardware of the controller. So instead of externally connecting a resistor, okay, we don't need to do that because internally we can do it. Okay, so I enable the internal configuration first, and then I decide whether it's going to be a pull up or pull down. So by setting the PS to 1, the pull select to 1, I'm saying that the internal pull up resistor is enabled. Okay, so what is going to happen here is I'm actually having a internal pull up resistor to the VCC by default once I configure that. So now with this circuit configuration, we can relate and see why this behavior is possible. All right, because by default it will be a 1. All right, when I read this pin over here, when I read this pin as an input, by default it is a high, and the moment I close the switch, I will create a short circuit to ground. So I will go to 0, and then when I release, it will go back high. Okay, so that is the relation between the hardware and the configuration over here. Okay, so that is basically the PCR. Okay, once that is done, you can configure the port D input, that pin as input. So to make it an input, you need to set clear that bit to 0. So we do AND with the complement of the mask. Okay, so I will not go through this in detail. We already went through, I think, a very detailed analysis of how the masking, the AND, the OR, the complement all works in one of the earlier lectures. Alright, so this is to make sure that that particular bit is clear. So once it is clear, we say that that pin is the input pin. Okay, now the last part here is the configuration and enabling of interrupts. Now, so since this switch is connected to the port D, all right, I need to configure port D. Okay, so in terms of priority and enabling, you cannot do that for individual pins in the port. It is across the whole port. Okay, so for port D, there's one overall configuration, and for port A, there's one overall configuration. So for port D, I'm going to set the priority. So you can choose any number 0, 1, 2, or 3, doesn't matter. Okay, because in this example you don't have any other interrupt, so this is the only interrupt. So whatever priority level you choose is still fine. So I'm just put a value of 2 here, but any other number 0, 1, 2, or 3 is fine. Okay, now clear pending IRQ. Okay, this is again part of I would say legacy code and general programming sort of approach, where you want to make sure that before I enable the interrupt, if by accident there is or for some reason there is already some chance that a bit is already set, that means the interrupt is already pending, even though you did not do it. Okay, you just want to make sure you clear it. So again, this is just idea of making sure that you start off cleanly. Okay, that means maybe some value that was there from some earlier configuration or something else, you do not let it affect your current program. So you just make sure you clear it first, and then finally I enable the IRQ. Okay, now these names, okay, sometimes you might think, okay, how do I know which name to use? How do I know it's supposed to be port D underscore IRQ, then small n? Okay, so all of this, okay, you can go to the definition here. Okay, let me. Okay, so over here in your MKL25Z4H file, they have enumerated all your IRQ based on the IRQ number. Okay, so you can see down here that your port D IRQN is labeled here and is already a value of 31. So as far as the code is concerned, it is more interested in the actual number, interrupt number. Okay, but the enumeration already gives us this name, so we use this name. Okay, so port D IRQN is actually 31 and port A IRQN is 30. Okay, so that is how you can relate the correct name to the number. Okay, even if you put here as 31, it still works. Okay, but of course, when you put 31, you yourself might forget what is 31 for. Right, so using the enumerated names is easier for us to relate. Okay, so we set priority, clear pending IRQ, and we enable the IRQ. Okay, so that is the configuration for the switch. Okay, so you configure your switch, configure your LEDs. Okay, then of course you write your code for all the LED control. That one you port over from last week's lab. Okay, so that's why I mentioned to you, you must think of making sure that your code is reusable. Okay, because you're going to build up your code. All right, so in this example, you're going to use those library functions you created last week to control individual LEDs. Okay, now the last part is this. Okay, so let me look at the main first. So in the main program, what I will do is I will initialize the switch, initialize GPIO, and I will switch off my LEDs. Okay, by default, everything is off. And then I want to, in my example here, I'm just toggling the GPIO. Okay, so I just toggle the GPIO. If I press, then the next time I press, I off. Then I press, it toggle, it start to blink again. So I'm not changing two colors here. I'm just either letting it blink or switching it off. Okay, and whether it's going to blink or whether it's switching off, that is controlled in the main program, but it is actually based on a flag, which is LED control, and that is in the IRQ handler. Okay, so now let's go to the IRQ handler itself. Okay, so the IRQ handler is actually very simple. Okay, so there's a question, do you copy paste those code? Okay, so your earlier code, okay, there's a few things you can do if you want to reuse. You can create that as a separate C file and then you can edit over here. So under your source group 1, you can edit as a C file, but of course when you do that, you have to make sure you don't have your main and all those other stuff, correct? Okay, so you can create from those functions you have created already. You can either copy those functions and put it in your current C file here, or you can group them as a separate C file and then include them in your project. Okay, and then you can reuse those functions here. Okay, so for your IRQ handler, basically the first thing that you want to do is you want to clear pending IRQ. Okay, but this is actually not necessary, like I said, because even if you don't do this, it will still work. Okay, I will demonstrate to you later. Okay, this is handled by default. That means the moment I actually detect the interrupt and I come inside here, the IRQ, there is a pending interrupt is already cleared. Okay, so this is actually done automatically, but I'm still putting it here as just good practice because that is part of the legacy code that was always there. Okay, but if you remove it, it's also fine. Now, this is the two things that I'm doing here that is critical to my actual application. One is, because this is the main thing, the LED control. The LED control is to either toggle between 0 or 1 to reflect back in my main program behavior. This other thing that I'm doing is I'm just keeping track of the count value. Okay, so you can later see that happening when I do the breakpoint. Okay, there's one additional thing that you need to do. You need to write a 1 to the ISFR register or that particular bit position. Now, what is the ISFR register? Okay, so let me show you here. Okay, so the ISFR register is a register, okay, that holds the interrupt status. All right, so the moment the interrupt is detected, there is a 1 written to this interrupt status flag register, which actually tells your NVIC that there is an interrupt from port D coming in. Okay, and what we need to do, okay, we need to clear this bit. And to clear the bit, I must actually write a 1 to it. Okay, the flag remains set until a logic 1 is returned to the flag. So you need to write a 1 to actually clear it. Okay, only when you do this, you are able to say that you have completed the interrupt and you're going to exit from the interrupt. Okay, if you don't do this, then you are forever stuck inside the interrupt. Okay, so I will demonstrate this as well. Okay, so this is an important step you must do. You must make sure you clear the flag. Okay, so the clearing of the flag is important. So you tell the NVIC that this has already been serviced. That means this interrupt has already been serviced, so I don't need to service it again. All right, so inside my interrupt, as you can see, the main thing is these two actions, and my main program is going to handle the toggling. Okay, so let me run to debug mode here. Okay, so let's see my LED here. Okay, so let me run the code first. So by default, it is going to be blinking the LED, and I'm going to press the switch now. I'm going to toggle the switch. Okay, so when I toggle the switch, of course, it doesn't seem to stop. Okay, okay, now it has stopped. Okay, this is, I think everybody knows the reason, correct? What is the reason? Why the first few times it didn't stop and then now it suddenly stopped? Yeah, correct. It is debouncing. Okay, so we have seen this before as well. Mechanical switch is going to generate a lot of pulses. Okay, so that is definitely an issue. Okay, so over that we can deal with it with whatever technique you want. But to sort of show you that it is really happening every time I press the switch, I'm going to put a breakpoint here, and I want you to observe this value over here. So this is the integer count value. So you can see that right now it is at 47. Okay, so 47. And if I press the switch one more time here, okay, you can see that now I have stopped, my program has stopped here at the interrupt service routine. This is the interrupt handler. So right now what has happened is the system has detected the interrupt and I have jumped to the handler. Okay, but now I have paused here. And now when I run, what I should expect is the 47 should become 48. Okay, so you can see that now it has become 48 and my LED is blinking. Now my breakpoint is still there, and I'm going to press the switch one more time. Okay, so now you can see that it is not affected by the switch debounce, because the very first falling edge already triggers my interrupt. Okay, but in a real life scenario, I have a lot more falling edges. Correct. So you keep on toggling between on off, and then you settle down somewhere. All right, but now that I put a breakpoint, the moment the first falling edge happens, I immediately stop. Okay, so I'm not affected by the remaining falling edges. Okay, and now again you can see that my integer is 48. All right, and if I continue with the program, it will become 49. All right, so this is a way you can check. Okay, because sometimes again, because of debouncing, you may not get the correct response or the behavior of the LED, but by putting a breakpoint, you can check whether everything is still happening correctly. All right, so this technique of putting breakpoint and examining your values, okay, examining the code is a very useful technique. Okay, it will help you a lot, okay, to check whether everything is correct. Because if you do this and it's not working, it could be the switch is faulty, the LED is faulty, or there is an issue with the code. Correct. So this helps you to narrow down to say that, okay, the interrupt is correct, the switch is correct. Okay, and then you can look at other things that could be an issue. All right, so that is basically what you need to do. So if I remove the breakpoint and I press, okay, again you will see that sometimes it triggers, sometimes because of all the debouncing, it doesn't quite trigger. Okay, but the code is working as expected. All right, so what you basically need to do is a slight extension of this, where you need to, instead of just on and off, you need to make sure that you sequence through the different colors, okay, as and when whenever you keep pressing the LED. Okay, so I think that sort of gives you an idea of how to go about with the lab. All right. Again, okay, the letter symbol in the counter over here, it is just the ASCII interpretation. Okay, so when it takes the value, it also interprets it as some ASCII value. Okay, and then it gives you that value, but you're not interested in that. Okay, we're only interested in the actual numeric value. Okay. Okay, so one thing I want to say is, okay, you have 1 week, okay, to sort of work on the code and do the demo. So don't rush through and just copy from your friends or you know or anything like that and just try to do the demo. Take your time to understand and really observe what is happening. Okay, this is a good opportunity to really learn all this stuff. Okay, and make sure you are proficient in it. Okay, so don't rush through. Okay, you have more than enough time. Okay, you have more than enough time to work on the code, try it out, you know, and within the group, okay, even though you're 3 or 4 member team, I hope all of you try. Okay, don't just rely on one of your friends to do all of this, okay, and then you do other stuff, right? All of you should try, even though you're going to develop the same code, it's fine. Okay, just make sure you yourself try, so you yourself get the confidence to do this. Okay. Yeah, so I will not go through all of this. This is what we already discussed. Okay, so in terms of timing, if you were to try and let's say probe the signal, okay, from the switch perspective, okay, you should get something like this, okay, where at some point of time you trigger the switch, okay, and you jump to the ISR. Okay, and if you look at the time that the main is occupying, of course, it seems like it is running continuously without any break. Okay, but if you were to zoom into this section, okay, you will see that there is a period of time where you are away from the main. Okay, okay, that means the main is not executing because you are doing the interrupt. All right, so again, this is the reason why we want to try to minimize the interrupt. Okay, because you do not want the main program to get delayed for too long. Okay, so that is where the idea of just using flags, okay, to indicate some action, and then you update the rest of the activities in the main loop. All right, now the other thing is, of course, interrupt latency. Here we do not look into it so much, but the This interrupt latency is basically the time to do all those hardwired stuff that we talked about just now. Okay, so of course, every time the interrupt is triggered, you have all of this hardware stuff happening, correct? So even though it's handled by the hardware, it still takes some amount of time, okay, before you can complete it and then you start executing the interrupt. So this is of course important in cases where you really want to minimize the amount of time. So if you have amount of time you waste, correct? So in situations where your hardware may be triggering the interrupt very frequently, then you need to rethink your strategy, right? Because if you have an interrupt that is always triggering, okay, then you waste a lot of time in just trying to service interrupt, and then the main program never gets a chance to run. So these are all things that you need to take note of. So that is where some analysis comes in. You will look at this in the tutorial, but the whole idea is, okay, what is the maximum frequency of interrupt that I can have? All right, and the maximum frequency, that means the interrupt frequency rate, is the CPU frequency divided by the number of cycles I take for the interrupt plus the overhead. Okay, of course, this is a very simplistic approach because you only factor in one interrupt. Okay, when you have multiple interrupts, when you have nested interrupts and all these things, it gets a lot more complicated, all right, to calculate something like this. Okay, but with just a single interrupt, you can sort of get an idea on what is the maximum frequency that you can have. Okay, but of course, when you try to max it out, what happens? If you try to max it out, it is not going to have time to do other things. All right, so that is where the utilization comes in. That means how much of the processor time is actually consumed by the interrupt. So that is given by this formula here, where you take the interrupt frequency, okay, and you multiply it by this, the addition of your cycles for your interrupt over the clock of your CPU. So this gives you an idea that what is the utilization of the processor time for interrupt. Okay, because you only have one processor and you're trying to share that one processor across all the things you're doing, your main task plus your interrupt. Okay, so if your interrupt only happens once a while, okay, then it's fine. Okay, and you keep it short, you don't see much of an issue. Okay, but in cases where your interrupt is very frequent and each time it takes up a lot of time, okay, then your utilization in the interrupt itself can be very high. Okay, then the main program suffers. Okay, so these are again things that you can just do some simple calculation, okay, which you will do in the tutorial just to have an idea of how to look at these numbers. Okay, so this are just the last few slides just to give us some thoughts about the interrupt itself. Okay, how much work to do. Okay, again, we always try to keep it simple. Okay, should ISR re-enable interrupt? I mean, in some cases, if let's say after the interrupt has occurred, do you want to re-enable it for other? Do you want to disable it, or you want to keep on enabling it, and so on? And how do you communicate? Okay, between ISR and other threads. So that is where the concept of a shared variable comes in. Okay, but at the moment you have a shared variable, you have other things to worry about. Okay, in terms of buffering and the race conditions. Okay, so this part. Okay, so let me come to this: sharing data safely. Now, sharing data safely. Okay, the first thing that we did is this volatile concept. Okay, so this volatile concept is again important, just to ensure that when you have variables updated in the interrupt, you want to make sure that you get the updated value in the main program, so you declare them as volatile. Now the other thing is non-atomic shared data. Okay, so this is what we call vulnerable to race conditions. Okay, a simple example of what is a race condition is in the context of a single-threaded system. Now, instead of a single variable, okay, let's assume that you have okay. So how do you think of race condition? Now let's look back at the same example, integer x, and I say x equals x plus 1. Okay, so we understand that this leads to three things. Okay, load. Okay, so again we will say load register R7 with x at R7 with the value 1, and then later you can do a store. Okay, so now this code is being executed in my main program. Okay, now let's assume that this x is also accessed inside my ISR, and in my ISR I'm going to say x equals to x times 5. Okay, so let's say this is the action I'm going to do here. Okay, now what will happen, okay, if I run this code here, okay, and after I do the first two steps, okay, after I do the first two steps, I get interrupted. Okay, you have to understand that this three assembly language instruction relate to this single line of C code. That means I'm still executing this single line of C code. Okay, so what would happen is this ISR will do the same thing. You will do a load, maybe register R6 X. Okay, then you will do the multiply operation R6 with 5, and you will store back. Okay, so right now at this point of time, I get the latest value, which is 5x. Okay, and this 5x is written into memory, correct? This is already updated into my memory space here. And after I finish, I return from interrupt. And when I return from interrupt, what do? I take the R7 value and store into x, which is actually x plus 1. Alright, so that is the problem. Okay, that is what we call a race condition, because you have a situation where you have a non-atomic shared data. Non-atomic means you do not have exclusive access to shared data. You did not protect X correctly, okay, because X was used in a sense halfway through in the main program, but I got interrupted, and also I updated X. All right, so then this kind of situation lead to very funny results. All right, so when you run your program, then you see that how come sometimes it's correct, sometimes it's wrong, and you can't figure it out because everything is correct. Okay, and why is because this kind of race conditions might only happen once a while. Okay, and when it happens once a while, it's very, very difficult. Okay, because you do not know what really caused the issue. Okay, so these are real issues that we need to deal with. All right, and when you move to an OS-based platform, you will see that it is a lot easier, okay, to handle this kind of situations, because the OS itself has a very good framework to handle this kind of atomic shared data issues. All right. Yeah, so this is basically what we talk about race condition, and to avoid race condition, right? Basically, a race condition is basically caused by what we call a critical section. That means a section in the code where you only want to ensure that one person is able to access it. That means if I come back here, if my main code here is accessing the X, okay, and I haven't finished with it, then I should not let the ISR take control of the X. Even though the ISR triggered, it doesn't matter. I should still deny ISR the ability to control X. Okay, so that is the idea of having or this idea of what you call a critical section, and you want to protect the critical section, okay, by some mechanism. So whenever I enter and exit, I must do some kind of checks whether I'm allowed to access this variable or I should not access this variable. Okay, so those are the kind of things that we need to factor in. It is more challenging to do it in a single threaded system, but once we go to OS, you'll find it a lot easier. Okay, so that brings us to the end. Okay, again for this lecture, basically we looked at the interrupt, okay, the concepts, the application to the board, all right, and the lab demo as well. Okay, so for this week's lab, I sort of showed you already what you need to do, all right, and I think it's manageable. The only thing, like I said, I'm always very concerned about is that soldering part. Okay, so for the soldering part alone, please try to check that you try to make sure that you get somebody who is really good, okay, who's confident to do it. Okay, if you want to practice before you do it, okay, always just ask Uncle Jalil for some small protobots, okay, and then you just try to do some practice on your own before you do the soldering. Okay, so within the team, I would suggest you just set aside one board first to do the soldering, okay, and use maybe that board for the rest of the development, and you can keep the other boards as spare boards. Okay, but if you want to use all the boards, also is up to you. Okay, so that is probably what you want to think about for the soldering part and the lab. Okay, so does anybody have any things you want to ask, any questions about the class or the lab or anything? Okay, if no questions, then thank you very much. Okay, I will see you all in the lab, or I'll see you all next week.